Don't applaud now. You have no idea if this is going to be good or not. All right. So, okay, cool. So yeah, I'm Scott Blomquist. I'm on Team Sharkbait, which is a Seattle area team, but I'm currently in Portland. So I guess I'm one of 3 approximately Portlanders who are here. And it's fun to be able to make the trip down and hang out with you guys. So first off, my title is just a little bit of an exaggeration, but I promise you'll get out of it what you hope. So if anything is an exaggeration, it's the analytic framework part. Like if you're expecting to get a number out from any slide in here, you're completely wrong. But at least it'll improve your subjective ability to assess your puzzles by showing you ways to find all of the things that teams could do wrong.
Can we look for a letter instead?
I can do, yeah. All right, no problem. All right, so what I'm going to do is I'm going to show you a framework that I've kind of been kicking around in my head for a long time called puzzle theory, but I haven't really talked to anybody about it, and I really wanted to fix that, and so I'm here tonight to fix that. The bottom line is it's only about half-baked, and I really want all of your help to finish fleshing this out, but I think there might be something here. The next thing we'll do is we'll apply it to a sample puzzle so that you can see how this works and see how bad I am at writing puzzles, but at least puzzle theory will tell you that. And then we'll talk about how you can use it to improve your own puzzle craft. So, without further ado, puzzle theory is, mathematicians in the room might be able to correct me on this, but I claim it's an unexplored branch of math, only recently discovered. What's in scope for puzzle theory is that it provides a framework for decomposing your puzzle into its component steps, which makes it really easy to figure out what steps you're expecting people to do, what steps they're going to invent as red herrings, and what sort of extra bits that you've left out there as dead ends that they could run down. And then possibly in scope for puzzle theory, because it's got kind of a broad name, is how to solve constraint puzzles, but I don't make any effort whatsoever to talk about that here. So let's start with talking about what kind of puzzle it is that puzzle clowns like us actually write and solve. I call them information reduction puzzles. Every word, phrase, definition, whatever in here, consider it completely in flux. I don't want anybody to adopt the first draft if other people in the room have better names. But, you know, again, I call them information reduction puzzles. I think it describes most of the game puzzles, puzzle hunt puzzles, mystery hunt puzzles, and so on. The bottom line is, in an IRP, solvers are provided with a set of data in some form, kind of an arbitrary form, and the goal is to distill it down through a series of steps to a word or phrase that you can wave on a wand or type into a shark or call in to a phone system. In an information reduction puzzle, there are 2 things worth talking about. One is the information content itself. I call those information streams, and we'll go more into that as we go. The other thing is, what do you do to those information streams? I call them transformation steps or simply transforms. So let's apply this analysis to a sample puzzle. I wrote this puzzle some number of years ago. It's actually shipped in a puzzle event, tested reasonably well, but there were a bunch of red herrings. I mean, this is not a work of art, but it's a nice self-contained puzzle that's pretty analyzable. So now we're going to play that dumb game where we play guess what the presenter wants us to say. And I'm going to say, go ahead and call out what you think might be the information visible. Don't think too deep, right? Like, don't do any analysis at all. Just describe what you see on the screen. What information is...
Count of the symbols.
Okay.
Of like symbols.
Sure.
Figuring out what cars they go.
Cars.
Yeah.
A location.
What country the car is from.
So we've already gone about 8 slides too far, but like if you don't think at all, you can clearly say this is a page of car badges, right? Like you could definitely safely say that without spoiling someone who's never seen this puzzle before. All right, so that's what we'll consider the obvious information stream at the start of this puzzle. All of this is very subjective. 2 different puzzle analysts are going to analyze a puzzle completely differently. That's entirely okay. You know, again, this is not, despite that I call it math, I think it's more mathy than actually math itself. And so there's room for judgment and subjectivity here. Don't tell mathematicians I said that. So the next thing we talk about is candidate transformation steps, or candidate transforms. And some of you have thrown out some really good suggestions for what we might do as a first step. We might identify the names of the manufacturers represented. We might describe the location of each of the badges. We might count occurrences of each badge type. So let's go ahead and apply those transforms in our mind. And we get to the point where one very important point is that an information stream that you already have never goes away, right? Like So we still have just the badges in their amorphous shape on the front page, and that might come back to haunt us in a later step. It's important to keep that in mind because, one, sometimes puzzles do that legitimately, and two, even if your puzzle doesn't, teams might not know that. Teams might go back and try using information that you expected them to throw away 8 steps ago in downstream steps in the puzzle. All right, so now that we've done that processing, though, we also have names, counts, and maybe locations. In this particular form of the puzzle, it originally was on a grid. In fact, this puzzle was inspired when I noticed that 36, the number 36, is both square and triangular. So I noticed that you could get 1 plus 2 plus 3, so on up to 8, and also 6 times 6 to be 36. So I was thinking, oh, I can, well, we'll get there in a second. But that turned out to be a horrible, horrible red herring. Teams literally took, okay, I'm making random number, some, insane amount of time longer. Go ahead.
N minutes.
Yeah, n minutes longer. That's exactly right. And n was big. Yeah. All right, so candidate transforms now, we've got counts, we've got names, things that you can do when you've got words and counts. Well, you can index them. You can index by location if it was still kind of the version of the puzzle where you had, this is the symbol in cell 3-3 or whatever. Okay, so once we've applied that set of transforms, we get this data. This is ordered approximately by first instance of the symbol on the page, but it's kind of unordered. But now we have an additional, so now we have 3 streams. Here I'm relating them, right? But the streams don't necessarily have to be related across like that. And now we can talk about a new set of candidate transforms. We still don't have a word or short phrase, like Leon is not going to be impressed at this point. So we can try ordering the last column in here by the count column, and we end up with the answer beauties, at which point GC or the wand or the shark or Leon or whoever ends up confirming. So once you're done with all of that, you can go back and say, okay, what did we learn about what people might do with this puzzle? And you end up kind of with this tree-structured thingy. You can, if you're a game theoretician, I guess you could think of this as a game tree, sort of. I mean, it's kind of decisions that teams are making. But the bottom line is every node in this tree is an information stream, and every edge represents a transform from one stream to another. And you see that there are some really early pruned dead ends in here, right? Like if you try going down the location path on this particular incarnation of the puzzle where the badges are, it's really hard to assign coordinates to them because they're, literally just kind of scattered onto the page. If a team tries plunging down the locations branch, they're not gonna be able to make progress, waste time there. They're not gonna be frustrated. Counts ends up being easy, and it ends up coming in handy later, right? But the bottom line is they're not burning time on a dead end that takes a lot of time, and so on. So you can kind of see how this shakes out. If you try indexing names into locations, prints itself again. All right, so now once you have this tree thing, yeah, go ahead.
Sorry, I missed something you said a moment earlier. Did you say that because locations is pruned, you don't have to worry about it, teams won't spend time worrying about the location?
Yeah, but I employed judgment there, right, to say that locations is pruned. There's no doubt about that. Like a team could invent a red herring there still, but if you look at that and say, oh, interesting, on this tree, I've drawn it as a dead end. Okay. Is there any possible way that I could cause that to not be a dead end? Like thinking like a team. Is there some ridiculous way I could assign locations? Okay, sure. You could count what pixel X and Y, the top and left edges of the symbol are at, but those are big numbers, don't look very alphabetic, right? Rational teams, not all teams, all of us are irrational.
Connect them in constellations.
Right, you could try connecting them in constellations, right. So absolutely, I mean, there's lots of possibilities here, and this is where judgment comes in. You're gonna end up with a tree that has some distractors left in it, and that's where you have to just sit and think, are there any things that I can do to head off these dead ends? Maybe I'm interested in sending a team down this particular wild goose chase and so on. Signs from this analysis that you've done so far now that might indicate that your puzzle is going to be bad. If the analysis tree is very broad, it means that there's lots and lots of stuff to try at every single state in solving the puzzle. We've all sat down in front of a puzzle like that before. CD puzzles often come to mind here, right? Where you've got, if you think about the entire breadth that you could consider, maybe artist matters, maybe track name matters, maybe the word that the track starts at matters, maybe the length of the track in seconds matters, and so on, right? So just by being handed a CD, you end up being able to find yourself a tree that's at least something like 8 nodes wide, unless you very aggressively prune. So like standardizing all of the track lengths to exactly 30 seconds. Employing tricks like if order doesn't matter, putting them in an obviously canonical order, alphabetization or something like that, so that you're signaling to teams, don't even bother here. This is a part of the tree that I don't want you to pursue. Actually, in the interest of time, I think I'm just going to let you guys read this slide to yourself. If you have questions about any of these in particular, I'm sure I omitted a whole bunch. I didn't really write the signs that your puzzle is a good puzzle thing, because it turns out that's a remarkably harder thing to generalize about. And that's where your expertise as puzzle designers is going to come in. One of my favorites is abuse of the aha transform. So, again, on the not so much math thing, it's really hard to numerically define the aha transform. But if you're counting on somebody to notice that all of these words anagram to the third character killed in a Shakespeare play, you're probably going to have trouble with teams figuring that out. And then finally, come talk to me afterward. This was the first puzzle that I wrote after I discovered that puzzle theory might be a thing. It has some interesting properties. Not a horribly good puzzle, but it's kind of elegant in the context of puzzle theory. So if you feel like you're a puzzle theory nerd and want to continue the conversation, come find me later. It is Jumbo Jet, yeah. All right, so now that he spoiled it, which is fine. The interesting property that this puzzle has is that it's what I consider one-dimensional. That is,
there's obviously 747 of them.
Right. You can't. Ladies and gentlemen, meet Rain Man.
I'm just assuming the ones that are off the edge of the slide.
Oh. Priceless. Yeah. No, that's absolutely right. It is in fact Jumbo Jet. Yeah. Okay. So bad but solvable. And then finally, if you're interested in puzzle theory, there's already a Google group with exactly 1 member. There's a PB wiki set up where I've actually started brain dumping some of this stuff, but I guarantee I'm not independently going to be able to come up with an exhaustive set of these transforms. But I think if we all put our brains together, we're going to be able to come close to listing all of the things that you should kind of have on your checklist as a puzzle author, as far as red herrings that people might find and so on. And if you want to continue a conversation about this or anything else, places to find me are, you can email me at scott@blomquist.st, or I hang out on a puzzle blog that's kind of thin on content right now, but I'm actually pushing really hard to develop it more this year, called puzzlehunters.com. There are also forums there. A lot of times there are better forums, more appropriate for discussions about whatever particular thing you want to talk about. But there are kind of underused forums there for collaborating on solutions to puzzles on Games Magazine, or Greg Broom's Panda Magazine, some of you might be familiar with. Anybody have any questions that I didn't cover? I mean, I know I kind of blazed through that, but yeah, go ahead.
So about the dead end thing, there's something. Okay, but I get it next.
Oh, very nice. So about the locations, and I think your formulation needs some way of capturing that the location has been sort of, I don't know, dealt with. You mentioned that you could if you have a bunch of strings, you could sort them alphabetically, and everyone knows, oh yeah, they're sorted alphabetically.
Yep.
I think your analysis needs some method of representing that, so that, if nothing else, so that you, the designer, knows that a good team will discard this information. They'll recognize that it's not trying to convey anything else.
Super good point. Yeah, like so. Yeah, you should post. And I'm completely not kidding. You should post that on the Google groups, and let's start having that conversation there. Because I want to capture all of this where people can go back and refer to it. But I think along those lines, one place where this is going to start getting really interesting is once people have kind of generated these trees in advance and then do the beta testing of a puzzle, like first draft testing or something, put it in front of real people and see where the tree was wrong. And all of the places where your predictions don't stack up to common practice are really good opportunities for us to say, hey, think of this. Advanced solvers don't get stuck in this class of traps, but consistently when I put this in front of less advanced solvers, despite that it's crystal clear obvious to all of us who have ever solved a destruction puzzle in our lives that this is not a destruction puzzle, maybe it looks like it to a junior team. Any?
So thanks for sharing all this. This is awesome. This is really cool. And it's also very familiar territory for me as a puzzle maker. I have kind of this internal mental map. I've never drawn a diagram of it. And yet I do think of puzzles in terms of layers. So I want to add a couple terminology as layers for what you've got there. And when we're designing one and we think of a node you want to prune and you realize this could be valuable information, sometimes we like to play with that, allow it to short circuit into a mini solution that redirects you to try one of the other ones. And I've been calling those signposts. And if our puzzle is missing signposts, you get a lot of frustrated head scratchers.
Absolutely, yeah. Yeah, so that brings up a really interesting point, that here I started with a single node at the root of the tree. But I think technically you can have several disjoint trees, right, in this family of things that comprises your particular puzzle. And maybe the most obvious descent solves for one of these signposts that sends you off. And before it was just a set of colored things. I don't know what to do with those, but once you get a signpost, it might answer that question.
Yeah, think of presidents or something.
Right, right. Makes a lot of sense. Yep.
So I think it started when we were playing in games. We came up with this phrase called billions to 3, and it became kind of a mantra when we were designing puzzles. And it's that when you're handed something and there's a billion options, you don't even know where to begin, right? It's just a frustrating puzzle.
So true.
And you need something to guide you to a handful of things you can try. And the first thing I thought of when you showed this slide was, it's a great representation to realize, have you solved that problem? Have you gone from billions of options to 3 that a team can reasonably try? And that's really cool, because I've never really thought about billions to 3 in depth, but I feel like that's what this talk was.
Yeah.
And then also, this graph seems like a great start for your help system, right? How do you guide people
that is such a good
along
point.
the right path? And then how do you guide them to the transformations?
Yeah,
for each
and
layer?
spotting the intermediate conformations that should be in the little Palm Pilot if you're doing intermediate conformations and all of that stuff, right?
Yeah, I have to say, when I
Super good
saw your
point.
title, I was a little afraid. I was like, oh man. But your talk has been awesome.
Cool,
So-
thank you.
So Teresa just brings up one other point in her comment. She called this a graph, and I think technically it's going to be a graph because there will be some streams that take multiple streams from earlier on.
Very good point, yeah. Well, and so kind of on your notation assertion that you made earlier, the fact that locations gets fed in here kind of marks that as a used node as well. And there's something in the back of my mind that tells me that an elegant puzzle ends up with no truly straggling data streams, right? Like everything got ticked off as, oh, I used this. And sometimes some of those signposts I've seen go unsolved before, right? Like a team intuits the thing and they didn't end up needing to solve it. I don't know. That might be something that you go back and solve later. Like if puzzles are if they trend toward very tightly constructed with no straggling data, it might be an interesting thing that points out facets of puzzles that you hadn't really discovered during the heat of battle.
I just wanted to we think about this all the time in terms of layers and everything. One thing you may want to look at adding to the graph structure, because this is fascinating, and John Owens from Advil and I have talked a little bit about how you even have this discussion. You know, he uses words like copacetic and pairings and orderings and math nerd. He's a math nerd. One of the things you may want to try that will help the graph language form is start from the very bottom of what does a solution look like? How do you graph a solution? It's not always a single node. Sometimes it's multiple nodes in concert, or sometimes it's multiple pieces. And so how you represent a solution is also important to how the whole tree sort of falls down and feeds together.
Very good point, yeah. Cool. Anything else? I'll stop taking up time. Cool. Thanks, guys.